Okay, question 13. Which of the following is Arrhenius base? Now remember, Arrhenius is that first simplest definition. Add it to water. Does it increase the OH minus concentration? That's a base. Now the only one here, that's a strong base. I put lithium hydroxide, right? That's a plus. That's a minus. It's a salt. That goes into water. Immediately, OH minus concentration goes up. The rest of these, that's an acid, that's nothing, sodium bromide. Methanol, now there's an OH bond in there, all right, but it's not polar enough to be a proton donor, which would make it actually a Bronsted-Lowry base anyway. That has to be a proton acceptor to be a Bronsted-Lowry base. But this won't even ionize because we'd have to have another oxygen attached. Then that makes this polar enough for that to happen. Actually, that oxygen would be attached there, not there, and that would then make this polar enough to ionize. But methanol itself will not ionize. It's just a hydrocarbon. So the choice here is lithium hydroxide. So question 14, another of the same type, but now we're changing from Arrhenius definition to Bronsted-Lowry base. And remember, Bronsted-Lowry base is a proton acceptor. And in this case, that's this one, because NH, H, two lone pairs up there in the struggle with water, that H to make NH4 plus. So ammonia is the proton acceptor, which makes it a Bronsted-Lowry base. And in fact, we're going to see amines again and again, right? N and H, H, and then we pulled off one of those H's, replaced with some hydrocarbon or something like that. That's the amine functional group, and that is basic. It will be a Bronsted-Lowry base. Okay, question 15 is which of the following acids have the strongest conjugate base? So here's what we're talking about, is that in each of these cases, in the presence of water, they undergo possibly an equilibrium. So it's an acid, because it's going to form a conjugate base. So that means it's going to form H3O plus, and then leave behind Cn minus. And then this, here's the acid. So that's the conjugate base. Now what are these other ones? These others, those are all strong acids. They're all strong acids, meaning that if I have HI, it doesn't battle for that proton at all. It goes totally to make H plus I minus. Never comes the other way. So this is a stronger conjugate base than any of these others. These are not bases at all. So the answer there is HCN. In question 16, calculate the pOH of a solution that contains 2.4 times 10 to the minus fifth is the concentration of H3O plus. So remember, H3O plus concentration when multiplied by OH minus concentration equals 1 times 10 to the minus 14th. So we're going to take H3O plus concentration, cancel on that side, and that will give us what this is. So that's going to be 1 times 10 to the minus 14th divided by 2.4 times 10 to the minus fifth. So OH minus concentration minus is equal to 4.17 times 10 to the minus 10, and pOH is then equal to minus the log of that OH concentration, so it's 4.17 times 10 to the minus 10. And in this case, that turns out to be pOH equal to 9.38.